Section 9.5 series.
Hey, this is actually pretty interesting stuff.
Okay, so a sum refers to a finite number of terms being added together.
Right.
Finite means countable, so...
Right. Even if it's like 100 jillion, you can still, in theory, count to 100 jillion.
Whereas you cannot count to infinity unless you're Chuck Norris, like we discussed in the last video.
Right.
So a series refers to a little issue with my grammar there. A series refers to an infinite number of terms being added together. So then you are talking about like...
And that is cool because, believe it or not,
sometimes you can actually find that sum. You'd think if you were adding forever that you would
add
be
up
able
to forever.
It would just like go to infinity, but not all of them do. So whenever we're dealing with sums and series, we have this thing called summation notation, which is just one of the coolest phrases ever.
And it's got a sigma. I mean, hello, we can all be frat kids.
Yeah, well, I'm not really a big fan of my own sigmas. That like with more practice, you get better at stuff in general. Like my curly brackets are, well, that's not a good example.
That was a horrible curly bracket.
But like that's pretty good.
That's not bad.
I mean, but
let's see a sigma.
My sigmas,
that's a little awkward, but it's not horrible.
But
we can work with it.
Anyway, so, and really you don't even need to, just as long as it looks kind of like a pointy E, we're good. So we use this notation to talk about, like, this right here would be some kind of expression or whatever that...
It would look like our functions look to us right now.
Right, like n squared plus 1 or k minus 3.
Right.
This bottom number, k equals 1, that is where we start.
Yeah, it tells you what number to put in to get your starter.
Yeah, we're to put in first, and then in up here could be a number, or it could be in, or it could be infinity, but it tells you where you're stopping.
Right.
And so we're going to practice in example 1 using summation notation. So.
All right, let's do it.
We have here 2 plus 5 plus 8 plus 11, ... plus 29.
Oh, all the way up to 29.
So this is stopping at 29. So we are going to have a number on top.
Right.
Our first term is 2, and then it looks like we're adding 3 each time. So that's an arithmetic sequence, which we learned in the last section. So before we actually start with the sum, we
got to get an explicit rule.
Right. So we start with 2, and then after that we add 3 each time, and so we said there was this explicit rule we could use each time. Well, now what we can do is we can think about, well, when I plug in 1, okay, I do get 2, so my sum starts, and you can use k or n or whatever you want.
Sometimes j's or i's will show up. Those are your normal summation.
K and n are really big though.
Right.
And then we can put this in as our expression.
Right.
But then we got to figure out what number we're ending on for 29. So to do that, Can't
we just set that equal to 29?
Absolutely, and then solve. So you'd subtract 2 over, and I'm going to distribute... Well, you don't have to distribute the 3, actually.
You could,
I could just leave it and then divide by 3.
Right.
So subtract the 2 over and get 27. Divide by 3. My equals. I have trouble here. This is going really badly on the equals sign front. Okay, so add 1 and you get n equals 10. That's the number that goes on top.
That's your stopper.
So we had to figure out for sure where we were starting, because sometimes it makes more sense to start with a 0.
Right. Sometimes, and you could write this one to start with 0.
You could, and what happens is if you go left a spot on where you're starting, which that's what 0 would do, then where you're ending would go left a spot, and this actually ends up, I think it goes backwards. Like we would put just in there instead of n minus 1, so it's like we're going to the right. It's really, it's something you have to get used to with some practice.
And some of these can be really challenging to discern as well. So it just takes some practice and time. And
yeah. So this is actually really nice that they gave us this information.
Look, they gave us the pattern there.
Yeah, that's the pattern we're going to use. And so we're going to put n plus 1 cubed. And then that means, because that's the last term, that n is where we're stopping.
Right.
And that can be confusing, but basically we're going to plug in all of the numbers until we get to some arbitrary number n.
Some made up number n.
Okay.
Some specific number.
Yeah. And then now we just have to figure out what number we're starting with.
Right.
Instead of what number we're ending with. So we would do the same thing as before. N plus 1 cubed has to equal 1. So what does that mean that n is? Well,
take the cube root of everything.
Cube root of everything, and we still have 1, and then you subtract the 1 over, and so see here, n equals 0.
Oh, looky there, it does equal 0.
And I feel like I don't know. Should we have used a different letter than N?
On the top?
On
the bottom?
No, on the bottom. Like typically our indices.
You
are
could still say
like
a K if you want.
And K.
Yeah.
Sorry about that. You having to write over it, but. So we start at k equals 0, we plug into k plus 1 cubed, and then we're going to stop when we get to n.
Right.
And lastly, C. So this one's...
Oh, say, can you see?
This is a geometric series, or series actually, because it's going on through infinity.
All the way to infinity.
And we're multiplying by -3. So let's write our rule for a geometric sequence.
Now pay attention because this alternates from positive to negative.
Right, so it starts with 5, and we're multiplying by -3.
How do I so good? What's it called, the big country or something?
And then we put an n-1 up here. That's what our
Right.
formula was.
Right.
And so now, if we think about our sum, because it has this ... that means we're going on to infinity.
Right.
So that's pretty nice. And if we think about it, if we plug in 1, we get 0 here, which makes that go away. That is our first term.
Right. So 1 works on this one. I feel like you're having some issues here, Mrs. Stevenson.
I think so. Maybe you may have to write on this one.
I may have to write after this. Nobody wants that.
There, right there.
Beautiful. There you go.